Hey there. Do me a favor.
Sit down.
Or, like, only if you want to. Only if you feel like it. I tried recording this video once already, and I've got a little gain knob on the back of this microphone that acts like this, and it blows out the audio to an ungodly degree. And it was on for the latter 50% of the video. And so here I am again, just recording it legit-wise, without the blown-out gain. I'm going to do everything in my power not to touch that fucking knob again. Or else I'll scream and cry, I guess. I'll kick and scream and cry. So, I love space. I fucking love space. I love learning about space, and I love learning things that make my brain hurt. There's a lot of big numbers involved in learning about space. A lot of, like lightspeed constants and just sheer unknowable numbers, unrelatable numbers, right? Like how wide the observable universe is, and zooming out further and further and further, and we are just, in the words of Carl Sagan, on a little pale blue dot. But there's a specific string of math that I'd like to do with you all today. I've already done it. I'm not going to write it all out. I'll probably jump cut around to where, hey, it's already done, because I don't want to sit here and do the math. That's what we have calculators for, and planning, like pre-planning. But I want to kick it off. This is very based on speed and light speed pretty heavily. There's one speed that I want to talk about, and I have a lot of whiteboard space. Last time I recorded this, I used only this section, and I have 3 of these, so I'm going to use 3 of these. All right, so we're going to start over here. We're going to work our way up. I've got little sticky notes with my math on them, so I don't have to keep cross-checking. But the fastest known man-made object, the record for man-made speed, recently was the Parker Space Probe. It is orbiting the sun currently, doing readings on solar flares and what have you. I don't know exactly. I'm not an astrophysicist. Also, I will preface, I don't have any degrees in this shit. I just think it's cool. So, I'm not going to feed you falsified information. This is all Googleable. But I'm going to present it in a concise form in front of you here, because I know a lot of people aren't going to do this math. A lot of people aren't going to sit here and do all this out, because this isn't just a readily available number, that you can just Google. So I'm going to do it for you. So the Parker Space Probe's maximum speed, this is the speed record for any man-made object to ever exist, orbited the sun its 17th time and hit this record of speed. And that record was 394,736 miles per hour. That's pretty fucking fast. That's speedy. Might I say, that's pretty zippy. Nothing else that we've ever had can ever come close to that. I mean, that thing is slingshotting itself around the goddamn sun. It doesn't surprise me. Stupid number. We can never reach this without something like that. And mind you, this is like a little tiny ass space probe that just has survey equipment on it. It's not like a craft with people on it. It's not a passenger aircraft. It's a small, tiny little telescope, or a tiny little instrument platform that has all these recording instruments for knowing about the sun and shit. So that's its max speed. Maximum speed. Speed record, 2023, a recent record. I want to come back to this in a little bit, because there's math we need to do here. The way we measure distance, aside from astronomical units instead of AU, because when we're measuring small distance in the galaxy or in solar terms, it's AU. 1 astronomical unit, is one distance between the Earth and the sun. So It's how we measure that stuff out. So we are 1 AU away from our own sun, but we only use that within respects to the smaller scale. Whenever we're talking about larger scale, we refer to it using light years. How far light, the fastest thing ever, like light or asterisk particles that have zero mass, because it's not just light, it applies to anything that doesn't have any mass. And I mean like literal zero mass. I don't mean near zero mass, zero mass. So there's other things in there, like I don't know exactly, but there's other particles that aren't photons that can move at light speed, or that must move at light speed because they have no mass. It's kind of interesting, because things that have no mass they physically cannot move slower than light speed, I believe. I don't know. Fact check me, please. If I'm wrong, tell me in the comments. But that's kind of cool. Like photons literally can't move slower than the speed of light. They have to. So the speed of light, as according to Google, or as according to, my official sources, is, if it's normally meters per second, I've converted it to miles per second because America, I'm sorry, I've converted it to freedom units, and that's how I'll be explaining the rest of this out in freedom units. If somebody in the comments expresses for me to convert them into kilometers per hour and edit those in, I will. But for now, miles per hour is easier for me because I am obviously American. So, light speed is 186,282 miles per second. Miles per second. Per second. So, already you're starting to see the ballpark we're in. This is a bigger number, yes, but this is per hour. This is per second. So now, how do we make this equal to that, right? So how do we get from miles per second to miles per hour? We'll multiply this by 60, because there's 60 seconds in a minute. And then we'll multiply it by 60 again to get the time in an hour. Times 60 to get the minute, times another 60 to get into 1 hour, right? Simple math. Luckily for you, I've already done it. Luckily for me, I've already done it. I don't want to do all this out. So, 1 hour of light speed travel, so this is miles per hour of light speed, it would be a whopping already number of 670 million, 615,200 miles per hour. That's the miles per hour of light speed. This is the miles per hour of the Parker Space Probe. Light speed, we're already in the millions. We're already in the hundreds of millions. So already super outpacing, but we'll go further, right? Because I want to have this equal, or like the end goal I'm trying to get to is our closest neighbor within our local group of stars. I believe it's called a cluster. The cluster might be galaxies. I don't know. Our closest neighbor, like the closest star next to us, is called Alpha Centauri. The closest exoplanet would be Alpha Centauri B, which is within the habitable zone, if I'm not mistaken. So it potentially could have life on it. We don't know. But Alpha Centauri B and Alpha Centauri, its parent star, there's 0 other things that are closer to us. That is the closest thing. That is 4.24 light years away. And we'll get back to that number because that has some pretty wacky modifiers. But we'll get to that. So, light years now we're measuring it. I want to figure out how many miles light will travel in 1 year. So to do this, we have the miles per hour. We need to multiply this by 24 to get how many miles in a day. And then we'll take that number, multiply it by 365 for how many days in the year. So, luckily for you, I've already done this math. So, times 24 to get the day, light travels in 1 day, and then times this, 365 for all the days in the year, and we'll get to see how many miles quantified light travels in 1 year that are described by us saying 1 light year. And that amount is 1 light year consists of 5,824,589,152,000 miles. A frankly absurd number that we can't relate to. We strictly can't relate to this, and I want to find a way we can. This is where we come back to this. So let's get to here. How many miles traveled in 1 year? Miles per year. 1 light year. Light travels at this speed, this many miles within the span of 1 year. Let's see how many miles this travels in 1 year, shall we? So, same math here. We're already in miles per hour, so we don't need to do the minute-hour thing. So, hours, so we go times 24 to get the day, and then times 365 to get the year. That comes out to traveling at this speed for 1 year. It's the same math we did over here to get this big-ass number. This speed, traveling for 1 whole year of nonstop travel, gets us 3,457,887,360 miles. Again, big number we can't really relate to. But what we can do now is we take these numbers, we take those two numbers, and now we divide them. Because now we see how many of 1 year travel of this speed fits into this. And that will tell us how many human years we would need to travel at this speed to attain this amount of miles, which is 1 light year, right? The results are kind of abysmal, but they equal about to 1,698.9 years. So it takes, to summarize, 1,698 years, 699 almost, years to travel at this speed to attain this amount of miles. So for us to travel at the fastest speed that we've ever attained with a man-made object currently, and to further emphasize, this is something that doesn't hold passengers. This is something that's not built to hold passengers. This is a tiny little thing. And so if we wanted to hold passengers for people to explore, or extra equipment to send a probe or something, it would have to be larger. Thus, we would have to make technological advancements to even get to this number. We're not even at this number, really. But technically, we are. By slingshotting ourselves around the sun 17 fucking times. But this number is theoretically attainable by humans right now. So, traveling at this speed for 1,698.9 years will get us 1 light year of distance. Now, remember what I said before, that Proxima Centauri and Proxima Centauri b, its planet, are 4.24 light years away. And so, let's do that math really quick. Simply, all we need to do is, this is 1 light year, so we times this by 4.24 to get the quantified number of miles. It's in the ballpark of 25 billion. So it's not even there's not much reason to write it out. I have the math here on the sticky note. I don't feel like writing all those numbers, so I'll just read it out to you now. So 4.24 light years of this distance is a grand whopping fucking total of 24,908,258,004,480 miles to our closest neighbor. So if we know it takes this many years to travel in one of these, so we simply take this times 4.24 over to here, and then we can quantify how many years it would take to get to Proxima Centauri b if we traveled at our fastest speed. So times 4.24. And that brings us to a very sad and, I would say, unfortunate number of 203.3 years. So, to travel to our next door neighbors within the cosmos, going the fastest that we possibly can right now, it would take us 7,203 years. 7,000 years. And now begs the question, how do you transport humans that far? The answer is we don't. Strictly, we don't. And so this, to me, rationalizes this big, scary number that we can't even relate to. I didn't even write out the 25 trillion one. Like, we're in the trillions here. It's ridiculous. This quantifies this for me. This helps me understand just how, I would say, not alone, but just how spacious everything is. Just how secluded we are currently. You look out in space, you look out at the stars, and it feels clustered. You know, it feels like, oh, that's all things we can go to, but they're not. The average star you look up at the sky is going to be way more than 4.24 light years away. And it is wild to me to, come to grips with this. We will never see Proxima Centauri b. Humanity, within our lifespans, within your lifespan who's watching this video, within your grandchildren's, within your great-grandchildren's, within your 10 generations down, we will never see Proxima Centauri b. We will never see humans on Proxima Centauri b unless we can come up with some form of, wormhole travel has been talked about, bending space around us to quote-unquote move faster is doable. I don't know if it's doable, but it's saddening to me. But this also aligns with my belief on extraterrestrial life. You know, people are always like, "Oh, do you believe in aliens? Or do you believe in little green men that have come to our world?" Yeah, sure, I believe in aliens somewhere in the fucking universe, but they've certainly never found us. They've never found us, dude. They're off somewhere. They don't give a damn about us. Look how secluded we are. Look at the closest neighbor. We're a rock whose closest neighbor is fucking 7,000 years away for us. You know what I mean? And then even if we found a way to make an object with zero mass, which is a kind of fallacy in and of itself, an object that can carry passengers but also negate their mass entirely, again, not really something that we can do. But theoretically, all in theory, if we did still do that and we were able to move at light speed, it would still take us 4 fucking years to get there, and that's moving at light speed. Nothing can move faster than light. There is nothing faster than light, not even gravity. The speed of gravity is not faster than light, by the way. It's near the speed of light or at the speed of light. But, nothing moves faster than light. Arguably, I think some sources are saying dark matter could potentially move faster than light, but I don't know. I don't know anything about dark matter. I haven't been really paying attention to that. But light speed is the speed limit of the universe, and it would still take us 4 years. That's like flying down the highway at the fastest your car could possibly go, and it still takes you a few years to get to your destination. Your car can't go any faster. It literally can't go faster. We literally can't go faster than light, and it would still take us 4 years. And then due to time dilation, 4 million years are passing. And so you could never tell anybody. Everybody you would ever know is dead. One dude travels at light speed for this amount of time. Earth as a civilization goes extinct. You know, like strictly 4 million years. 4 million years is like, I don't know. That's a number we can't even quantify. Like truly, which is why I like coming to this total, because this is something we can understand. So all this is to say, here's some big scary math. We're alone in the universe, or not alone. We're pretty secluded. We're a little isolated. This number feels scary to me, and I think y'all should feel scared too. Thanks for sticking around. Thanks for watching.